Now let's, after this more conceptual hardware details, this look at the hierarchy, we can also take a look at how to actually do the thread affinity settings in OpenMP and the pinning in MPI. And for OpenMP, so this is the feature of your programming language to run your calculation on multiple threads. There you can set the pinning of the threads, and pinning means that a thread is only allowed to be executed on a certain set of cores. For example, one thread per core, and it is not allowed to switch to a different core to be executed. And this is especially bad if the thread would move to a different NUMA node, because then it would need to access data that belongs to a different, to the previous NUMA node. But in general, it's a good practice and in general improves performance to have your threads pinned. And another reason is that it removes a certain variance in the performance of your application. So else you would have quasi-deterministic movement of your threads. And if you run the same application unpinned multiple times, you would see that you would get different or slightly different performance. And this variance you don't want to have. So what can we do? We can, in a compiled OpenMP program, if it's programmed properly, you can set these environment variables, OMP places, and with this one you basically decide the granularity of the pinning. So you can say one thread should only be on one core, or for example, it should only not leave a certain socket. Or you can very precisely define these groups here. For example, here CPU cores 0, 1, 2, 3 are the first place, and 4, 5, 6, 7 are the second place. There's also these shorthand notation for that. So this is how we define the groups that we have for the pinning. And then we can enable the pinning with the OMP proc bind environment variable. We can set it to false to not pin, or we can set it to true to pin and have an implementation defined default for the pinning, or we can say it should bind them consecutively to the places, your threads, or spread them around the places. And there's another environment variable, OMP display affinity. You can set it to true to let the application at the start print the configuration of the pinning. So you can double check if the configuration is correct and as expected. Let's take a look at an example. In this small example, we have a system with 2 sockets, and each socket has 4 cores. And in this case, there are also 2 threads can run on 1 core. And we set the num threads environment variable to 4. Therefore, 4 worker threads are created for the OpenMP calculations. And then we set the OMP places to cores. Therefore, we're considering each core one place. And then we set it to close. Therefore, the 4 worker threads are then distributed consecutively to the places, to the first 4 places on one of the sockets. So we're basically just filling up the first 4 cores with our 4 threads. And here is another example. Here we have again 4 threads, and we define as a place socket. Therefore, we have 2 places, the first socket and the second socket, and then we set it to spread, and then they're just spread around these 2 sockets. So 2 threads per socket. So what is the advantage, disadvantage here? Let's assume that in your application, the threads are talking a lot to each other. So they have to exchange a lot of small messages. Maybe then this could yield a better performance because they are, all of them are one socket. So they can then all, the communication doesn't have to go through the um, socket interconnect. Let's assume a different program, and in this program there's a lot of memory traffic going on from the threads to the memory. And here, depending on how many memory channels you have, if they would be on one socket, they would have to share the memory connection here, and by spreading them on multiple sockets, you can also use the memory connections that are on the different sockets. And then this would give a better total memory available memory bandwidth that may improve the performance of this certain kind of application. And then you can also decide the pinning for MPI programs. As explained, MPI is used to start multiple processes on one or more nodes, and these processes then can talk to each other by exchanging messages. This is why it's called the message passing interface, and there are multiple implementations, for example, the OpenMPI implementation or the Intel MPI implementation. And here's also, you can set the pinning, and this means that one process will then be pinned to a certain set of CPU cores. And what we can do, we can first also figure out with the sinfo command, you will get a list of the compute nodes, and you find that the information, how many sockets per node we have on the system, how many cores per socket, how many threads per core. So in this Nocta 2 example, it's 264.1. On Otus, it would be 296.1. And then you can define again the scheme of distribution to these certain levels of the architecture. So the schemes are block and cyclic, and this is basically the same idea as with OpenMP with close and spread. Block fills these places consecutively, and cyclic then iterates. And then we, for very detailed configuration, there's a distribution argument that where you can then define on these levels of configuration for the nodes, the sockets, and the cores, how these threads are, or how the MPI processes are distributed. For example, on multiple nodes, you can say cyclic. On multiple sockets, on the socket level, you can say, in this example, blockwise. And then on the core level, again, you can specify cyclic. And this way you can also specify how the processes are distributed. And then with CPU bind, you can again specify if they should be pinned to cores, so one process per core, or to sockets, or to the NUMA domain. Therefore, it knows the number of CPU cores per NUMA domain. And again, here's an example for a compute-bound application. You maybe want to pack the threads together as explained. And for a memory-bound application, maybe you want to spread the processes over multiple sockets. And if you're running job, then at the beginning of the job, you will see this output here that basically explains how the tasks or the processes, a task as a process, are pinned to the cores. So for every task, you will see then the task ID here on which node they are running, a local task ID, and then a core mask that basically defines that here the first task is pinned to the first core and the second task to the second core. And if one task would be allowed to be running on multiple cores, then it would have multiple Bs here in this core mask. So there's more information about the pinning with Slurm in the Slurm documentation. Okay, before we continue, let's take a small, short look at the exercise. So the main part of the exercise was this stream benchmark thing, and the idea is to run this memory bandwidth benchmark with these different configurations, and it changes where so the idea is to pin, use the numactl command to pin the threads to some NUMA domain and the data placement to a different NUMA domain, or to the same, or use different configurations, and also look at different threads to see how these options, so number of threads and the pinning, change the achievable memory bandwidth. So this is basically a memory bandwidth benchmark that tries to read some data, do a few calculations, and then write the data back. And so with a certain specified pattern. So we see here there are different configurations. Some are no pinning, some are pinning to the first socket or use memory on the second socket, and so on. And we can, so in the code, it's basically just a combination of using these parameters to set how many threads are generated or used by the benchmark, and then change these pinning configuration with numactl and then run the benchmark. And if we take a look, so you will find here a link to the solution branch, and here you will find this b_solution file with a sample script and some sample values. And as we see here, if you're only using one thread, then this one thread can only achieve like 64 gigabyte per second. So there are 12 channels per CPU. So in total 24 channels, but one thread cannot create as many memory accesses as necessary to use the complete bandwidth of these memory channels. And we see if we are using more threads, then we actually have a higher memory bandwidth. And or if we go up to 96 threads, then we can achieve 620 gigabyte. But here with no pinning. Or we can then use a different kind of pinning. For example, the threads are running on the first socket and are using the memory on the second socket. And here we see this bottleneck between the two sockets. Or we can achieve higher bandwidth with a little bit more threads. So this depends on what exactly the threads are doing. If you really need 192 to achieve the highest bandwidth or not, so this is a configuration thing, and also how exactly the program is is developed, is implemented. What's important to see here is if we are using no pinning or pinning makes a difference in the performance, and it also makes a difference in the variance. So for example, here are some other values from my run, and as we see here, for example, here we have the same configuration, but a different performance achieved simply because there was no thread pinning and no data placement. And then, for example, different number of threads on different sockets then behave differently because then they share a different number of memory channels and so on. And if you are doing benchmarking, this can be a source of variance that you do not want to have. Or if you try to debug performance, because you try to figure out where is the performance problem. And if you have then varying performance because of this other reason, then this makes it really hard to figure out what your application is actually doing.